Okay, we'll go ahead and get started. I would presume that if you had, well, you've been in here for a few minutes now, and you look up there, and oh my, that looks rather intimidating. Well, I don't know if you'd say intimidating or there's a lot of information up there, but it'll go faster going over this than what you think. And when we're talking about alcohols and their reactions, what did we spend time on yesterday? That was so important. Yes, recognizing what type of alcohols you have, because depending upon which alcohol you have, what you are reacting it with, okay? So then from prior knowledge, where have we seen oxidizing agents before? It is on one of your flow charts. Now, you don't need to be writing all this down in case you're wondering, because it is on your flow charts. This is just something for me to give you an introduction. Sorry, what?
Is it one of those up there?
It's two of the three, but it is this one that's on your chart, okay?
It's the K2CR04 and the K.
Okay, all of these are oxidizing agents. It's just that these two, the top and the bottom, I wasn't thinking when I wrote this, I should have flip-flopped those. But these are the two most powerful ones, okay? Well, of what you see up here. So this one isn't quite as a powerful oxidizing agent as what we see with those, okay? So then, if we are doing dehydration reactions with alkenes, okay, it's the temperature ranges that are so important when we're looking at these alcohols, because if it's at this temperature range, okay, we're going to dehydrate it to an alkene. If it's at this temperature range, then they get changed to an ether. Now, you have to be aware of which type of alcohol you're talking about, and that's what this is referring to here. Okay, so I think the place to start would be 399. And it says section 1310, okay? And then what you see there, it says the formation of ethers by dehydration of alcohols. Now, you might be thinking, well, we just talked about alkenes. We mentioned that. Why does it not say anything there? Well, again, it depends upon the temperature range that you're referring to, okay? So the discussion in section 13.6, which we haven't quite made it that far yet, on the dehydration of alcohols to alkenes was an oversimplification of primary alcohols. Heating a primary alcohol in the presence of an acid catalyst, see this is highlighted, okay. Acid catalyst products not only an alkene but also an ether, okay? So what you see there with that propanol, we got those three carbons, if it's a higher temperature range, you're going back to what we see as propene. But if it's at a lower temperature range, and I can't explain it, the best way that I can describe it is, it was a type of percussion instrument that I think you just call it a snap, maybe. You slap it, but yes. So what happens, and I try to do this with my elbows, that here's your pivot joint right here, and then it's just the opposite. What you see happening here is now you have two sides of your alkyl groups if it's at a lower temperature range. Okay, so as you're looking at this, let's just read a little further and then we'll make sense of that. Okay, so intramolecular dehydration, even if we didn't go any further, dehydration, what does that mean to you? Yeah, you're going to be removing water, okay? In the form of alkene completes an intramolecular dehydration to form the ether. In intramolecular dehydration of an OH group and a hydrogen atom are removed from adjacent carbons in the alcohol molecule. In intramolecular dehydration, the OH group and the hydrogen atom come from two different alcohol molecules. The reaction can be directed toward the production of alkene or the production of an ether by controlling the reaction temperature. So that's why it says that in the alkene, if it's 100, now I suppose you could say if it's in the 170s, they just use a line here, say 180 degrees, you're going to dehydrate to an alkene. But if it's at lower temperature ranges, maybe down to 150, now you're going to start forming ethers instead. Okay? But unlike primary alcohols, secondary and tertiary alcohols do not form ethers when heated with an acid catalyst. Intermolecular dehydration to alkenes is the major product at all temperatures. Okay? Alkenes is the major product at all temperatures. Secondary and tertiary carbons are too crowded because of the attached substituents to allow pairs of secondary or tertiary alcohol molecules to come sufficiently close together to undergo intermolecular dehydration. The effect is sometimes called steric hindrance. Okay, so with what we see here, okay, now I need to look at that again for just a moment. So I was just a little confused because I know that one of these is going to form an ether. Which one would that possibly be? It's going to be the bottom one because it's at a lower temperature range. So then what happens, like I said, we was trying to form, what did you call that, a snap? Okay, so a snap is a type of percussion instrument where there's a pivot joint here, and then, I don't know, I suppose you could say that's just about as accurate as anything. You lift it up, this comes up, then you go forward, then this goes back down, and then it snaps, okay? But the reason I like to use this as an example is if this is our oxygen atom right here, okay, that this is going to go all the way around now. So we could say that this is C2 with carbons, and then this is C2 with carbons. So here's two carbons here, and then here's our two carbons on top. So then when this comes all the way over the top, how do we know we're dealing with an ether? Well, true, but when you're looking at the molecule itself, how do you know you're looking at an ether? Yeah, there's going to be a single bonded oxygen in the middle. So what we see happening here then, okay, would be, although they use propanol on page 399, but the concept would still be the same if we're talking about ethanol. So here are our two carbons, okay? So at this lower temperature range, that hydrogen then is going to disappear, and you could say, well, where does it go? I really don't have an answer for that, because here is our oxygen, okay? And then because this is a lower temperature range, this then forms on the other side. Now, notice one of the things we said from an earlier chapter, we're not concerned with balancing each side of the reaction. It just does this. I don't know how, I don't know why, it just does. And that's something you're just going to have to accept, that this is what happens. So if we were going to change the temperature range on this, okay, could we possibly form an alkene from this, do you think? Because we just put this up as at random. But what happens if we were to maybe say, well, let's maybe heat this to a little higher temperature, closer to 180 instead? We're certainly not going to get an ether because the temperature range is too high. So then, what did it say about what gets removed then when we're talking about dehydration? You're going to remove water, okay? So then if we had this over here, okay, notice this would get stripped off of there, so there's half your molecule for water. So what would we possibly be missing? That's what we're going to get, but that's not what we're missing.
The second hydrogen.
Yeah, a second hydrogen. So we're half right there. So then what we'd see happening here, okay, that's going to disappear. Now we're going to form an alkene, but we're just not quite right here. First one has 5 bonds. So then we say, well, that's got to come off then too. Okay? So, and that's probably a little difficult to see on the first time through. So this is on your reaction charts. Maybe that's something that we have an introduction here, and then we'll get these out for sure on Monday. We just want to give you this introduction. Questions on what we see here. But what's the difference between these two compounds other than the number of carbons? Your reactant side, not your product side. Well, that's true, but the reactants, not the catalyst or the products. Okay, well, okay, so let me get rid of this. Now, when we look at the difference, we're reacting the same thing. Someone said it out there. Right. So this top one is a secondary alcohol, and this bottom one is a primary type. Okay? So these would follow similar pathways, but what would happen if we do this? We want a lower temperature range for that. Well, can that form an ether? The answer is no, okay? Because remember that snazzy diagram we had of that snap? It means you have to have a mirror image on both sides. You'd have to have 2 carbons over here and 2 carbons over here. That works on a primary alcohol. On a secondary alcohol, that just doesn't work. It'll still react, but it's not going to, for our purposes, it's still going to react, but it's not going to form an ether. We're still going to dehydrate it, but what happens when alcohols get dehydrated then? They form what? And we just did it here. Nope, not ethers. I should have said, what happens to secondary alcohols when they get dehydrated? Yes, because primary alcohols can become ethers. But secondary alcohols, when they get dehydrated, it's going to form alkenes. So then what that means then, okay, same process. That gets taken off of there. Okay, so there's half our molecule. So then it's at that time you would have to say left or right. Okay? So then, since you said left, we would take this guy off of here now. There's our other half. And then we've got these 4 carbons. Okay? We can safely put that one on. We can safely put those on. Whoops. Nope. Because that took that bond and everything. We can safely put all of these on. Okay? So then what has to happen, that double bond, is that going to occur here or here? After the second one. That's correct. Because between these two, this gets stripped off of there. We're going to form a double bond here. This still remains a single bond. And then we just have to do one more thing on that second carbon. Yes, because this hydrogen is still here. Okay? That's why recognizing secondary alcohols, primary alcohols, and even tertiary alcohols is so important, because they're going to react differently with different types of catalysts and temperature ranges with whatever it is you're reacting that with. Okay, last thing I want to mention, okay, we'll just briefly take a look at it. We're not going to do anything on the board. I just want you to see it, and that is to back up to page 390. Okay? So, oh, maybe it's actually, yeah, that'll still work. Okay. Because, why does it, I know why it says stage 2, but I just want, where does it say stage 1? Okay, but they still have the reaction mechanism on there. So at the top of page 390, what type of alcohol do you see there? It just says R, 2 hydrogens, and then an OH group. So that's going to be a primary alcohol. Okay? Then notice it says stage 1, and then over that arrow, what do you see on top of that arrow? It just says MnO4 or CR2O7. Okay? So that's potassium permanganate and then potassium dichromate. That's where these two come in. Okay? And that's why, like I said, I should have flip-flopped those so this one's on the bottom, because this one just doesn't quite have as much power or oomph, would you call it that if we're Norwegian? Because sometimes, yeah, your sister would say oof all the time, so that's got to be Norwegian. Okay, so we could flip-flop these two, and that's why we have the line here saying, okay, these two are very powerful oxidizing agents. So it says in stage 1, what happens to that primary alcohol then? What does it form? It says carbonyl group in blue. It's going to form an aldehyde, but that's not where it stops. That's going to keep right on trucking. It's going to keep right on going to stage 2. And when that happens, that primary alcohol not only turns to an aldehyde, but finally ends with what? A carboxylic acid. Now, the only way that that does not make it all the way to the end is if you're working with this middle guy. That one just doesn't have enough to push that all the way through both stages, where these two do. Okay? And then finally, what do we see about halfway down? It says secondary alcohol oxidation. What happens to secondary alcohols? What do they get turned to? Ketones. And that's all that they do. Okay? And then notice, does it say anything about tertiary alcohols? They mention it, but does it show any reactions on there? No, because tertiary alcohols cannot be oxidized. They just can't. It's just physically impossible. Because what you see happening is there's not a hydrogen on that carbon where it needs to be stripped off of there. And that's why spending time on primary, secondary, and tertiary alcohols is so important, because you have all of these things going on, but they are on your flow charts. The reason you don't know how to utilize them is because you haven't been taught that yet. Okay? So sometimes you start halfway through a mechanism, because you can start with an aldehyde and then oxidize that, or you can start with a primary alcohol, oxidize that with this here just to get the aldehyde, because it just doesn't have, again, enough power to keep right on going. Okay, so we have a lot of moving parts here, but we will make sense of that on Monday. All right, so even if I said any questions, you might say, I have no idea what to ask. This is maybe a lot of information to absorb. But front row, middle row, back row. All right, that's all I have. We'll catch up to you next time.